Recording in progress.
So, hello everyone. I think it's officially time to start, but maybe we'll give 1 or 2 minutes for some people that might be confused by Zoom links or time zones or whatever else there's to be confused about. So my name is Christophe, and I work at the University of Twente in the Netherlands. And I'll be the main chair for the session. In case my connection drops out, we have Massimo as a backup chair. I guess that's the way it's now. We're trying to do things. It's a little bit stormy today in the Netherlands, so maybe if something hits some internet post, things, let's say my connection could break, but I think it should be fine. Yeah, I think a few more people are joining. Maybe maybe we should just go ahead and start. The first speaker is Professor Martin Weitz from the University of Bonn. Will be talking to us about dissipative phases of photon boson-Einstein condensates, and I'm really looking forward to your talk, Martin. Please.
Okay, so thank you very much for the introduction, and I also thank the organizers very much for the invitation. So let me just switch on to my pointer. Okay, so the title of my talk is dissipative phases of a Bose-Einstein condensate of photons. So I will speak about a Bose-Einstein condensate of photon generated in an optical microcavity. So that's our experimental system, and I will speak about more recent experiments on a non-emission phase transition where between several dissipative phases of the photon condensate. So to begin with, given that this is a laser physics sessions, let me here start with a summary slide of coherent optical emitters. Here on the bottom scale, so both lasers and Bose-Einstein condensates in general are in weak coupling. In a normal laser, one has no thermalization at all or little thermalization. This basically means that photons first leak out before they have a chance to thermalize. On the other hand, if you do have a thermalization mechanism and the thermalization mechanism is faster than the cavity decay, then if you have a minimum frequency of the cavity modes, then consider there's a possibility that can be a condensate. I will talk about that in more detail. And what is interesting that on this scale, old bulk semiconductor lasers, they are a little bit more to the right than usual lasers. They're not thermalized, of course, but to understand their spectra, one had to understand things like a thermodynamic relation between absorption and emission, the so-called Cannon-Stefanov relation. This was known in literature. Historically speaking, development went to the left. What one was doing in the semiconductor industry, one was increasing the output coupling to get more power, and so one moved more into the non-equilibrium range historically. Okay, so all this is at weak coupling. At strong coupling, polariton can form, which are mixed states of matter and light, and depending on whether you have thermalization or not, you'll either have a polariton laser or polariton DC. Okay, so regarding the introduction, the Bose, this is generally on the ground state of bosonic ensembles. The ground state, or more precisely, the minimum energy of cold atoms in 3 dimensions is Bose-Einstein condensate as if it's bosonic atoms. So what you see here is a series of time of light images when cooling atoms through the VEC phase transition temperature in the nanokelvin regime. You see the macroscopic representation of the ground state. Now, what happens if you're trying to do the same experiments now with photons, one as particle of light? What then happens is the following: it's getting dark. The photons go away. Photons in free space in 3 dimensions have well, normally there's no chemical potential. The photons are not conserved particles. And if you cool that, they just vanish. The black body spectrum of photons at 0 kelvins is the absence of photons. So that's not a very interesting state of the light field. So how can you do better? There has been earlier work related to a photon Bose-Einstein condensate, and the first work that I'm aware of is a proposal by Sildovich and Levich from 1969, who proposed a photon VEC in Compton scattering of a thermal electron gas. So what was the proposal was to scatter photons of electrons of thermal equilibrium in the plasma. And the prediction was that you should get a shockwave structure plus a thermalized cloud, and the shockwave structure should resemble VEC. So this was never observed experimentally. What does work experimentally are exciton polariton condensates, which is which is a whole field which operate under strong coupling. The excitations then are half matter, half light, and in a semiconductor microcavity in one is an equilibrium for the condensed part. What is more close to our experiment is a proposal for photon fluid in a nonlinear resonator by Ray Chow. So what he wanted to do is thermalize photons by photon scattering, very similar to atom-atom scattering, atomic physics VEC experiments. So in free space, the cross-section for that is basically 0. And his idea was to enhance it by putting an atomic gas. The cross-section still was too low to obtain efficient thermalization, but I still think that this is a very nice proposal. Okay, so that's the outline of my talk. In our system, what we do is we use a dye solution optical field, optical microcavity, as I mentioned, we with the cavity change the dispersion relation from the usual linear to quadratic, that is matter-like, and we thermalize light by absorption and re-emission events of the dye molecules. I will first talk about the thermodynamics of system, and then on how to obtain a Bose-Einstein condensate. With that, it's 2-dimensional photon gas. I will then talk about more recent experiments. That's refers to the title of my talk on a non-emission phase transition for such a photon VEC, which is dissipated between dissipated phases. And finally, I will talk about a test of the fluctuation dissipation relation for this quantum gas of light. Okay. So that's next on the principle of our experimental machine. We, as polariton experiments we also use an optical microresonator, as I was mentioning, to modify the photon dispersion. In our case, it's a curved mirror microresonator, and the spacing between mirrors is very small. It's an integer number times half the wavelengths. And for the sake of simplicity, let's say that it's integer number n equal to 1. Then it's very clear that very long wavelengths do not fit inside this microcavity. So there's a maximum wavelength or minimum frequency of the light to fit inside. So we get a low frequency cutoff, similar as in a microwave waveguide, which is for the TM00 mode, the n equal to 1 longitudinal mode manifold in this example. And on top of that, it's a higher transverse modes. And here at some point, the n equal to 2 longitudinal mode manifold would set in. The dispersion relation is that then not anymore linear as a free space, but while we have this low frequency cutoff, and on top of that, it turns out to be quadratic. So next, we fill in our microcavity dye molecules in liquid solution, and we obtain thermal equilibrium of the photon gas by repeated absorption and re-emission events on the dye molecules, as I will explain in more detail in the next slides. So that's a typical spectrum of perylene DIMIT. That's a typical dye that we use. You see here both the absorption and the fluorescence spectrum, and it now turns out that the ratio between the fluorescence and the absorption has a Boltzmann-like scaling. With this, you can describe that as Stokes shifts that we see here. So proportional to the e to the minus h bar omega divided by kBt. H bar omega is the photon energy, kBt is the thermal energy. If that is fulfilled, it makes physical sense that you can get a thermalization. So you couple a thermal environment to the photons, and can also mathematically show that the asymptotic state then is a Bose-Einstein distribution. But what's the background of this Kenner-Stefan application? This here is a simplified model of a dye molecule with an electronic ground state and electronically excited state, and on top of it, it's all these rho vibration levels. And now it turns out that every 10 to minus 14 seconds or so, a solvent molecule collides with the dye. And this is, of course, much faster than any electronic processes. And because of that, not just the ground state rho vibrational manifold, but also the excited electronic manifold thermalizes. And we have a thermalized distribution both within the ground and the electronically excited state manifold. And this thermalization then also imprints on the spectrum of the absorption and re-emission events. Also basically, if you add the corresponding absorption amplitudes between the sublevels and the emission, and you look at the line shapes, you obtain this Kenner-Stefan Boltzmann-like frequency scale. And the temperature that comes into play is the internal rho vibrational temperature of the dye. And this, of course, equals the kinetic temperatures. And this, in our case, is at room temperature. So what happens if you absorb a high-frequency photon? Before emits, it relaxes to a lower vibrational state, and you get a Stokes shift. In free space, after a repeated of such Stokes shifts, you run out of resonance, and then the thermalization stops. But in the microcavity, we have a low-frequency cutoff, and we get a thermalized spectrum on top of the low-frequency cutoff. That's a scheme of the thermalization. So in the microcavity, we have several absorption and re-emission events on these dye molecules. And this thermalizes the two transverse degrees of freedom of the wave vector, the longitudinal wave vector that's fixed due to the low frequency cutoff. So what we effectively do, we couple a two-dimensional photon gas, the two transverse degrees of freedoms. There's two dimensions left. So we couple a two-dimensional photon gas to our dye solution, which acts as a heat bath at room temperature. And on this slide, I want to convince you that the trapping of photons in such a microcavity is formally pretty similar to the trapping of atoms in the cold atom experiments. So here you see the dispersion relation of free photons and that of the photons at the microcavity. And it turns out that we, in addition, have a trapping potential due to the mirror curvature. The reason for that is if the photons move to the side here, and due to the curvature of the mirrors, the spacing here on top is smaller than in the center. So that means in the center, the photons can have longer wavelength, that is lower photon energy. So in thermal equilibrium, photons rather remain in the center. And what you do is imprint a trapping potential to your photons. And with that, the system becomes formally equivalent to a two-dimensional gas of massive photons with such an effective mass, one can show quite easily. And for such a system, it's known that VC exists if you put more particle than a critical particle number, which is pi squared divided by 3 times kBt over h bar omega. Omega is the vibrational frequency squared. And if you put in numbers at room temperature, you arrive at 77,000, which is a reasonable number. So you don't have to cool to the nanokelvin regime. The reason for that is that our effective mass is relatively small. It's associated with the photon energy and mass unions. And because of the effective mass is small, the vibrational frequency is high, and you can make this ratio kBt over h bar omega to be a reasonable number in that room temperature. Okay, so this is our experimental setup. Here you see the scheme of the microcavity. The spacing is not lambda over 2, but 7 times lambda over 2, but that works as well. So here on the right-hand side, that's a photo of the microcavity. And we pump the microcavity with a laser at 45 degrees angles, and we analyze the light that leaks out both spatially with a camera and spectrally with a spectrometer. And this is typical experimental data, which was published a little bit more 13 years ago now. So on below the threshold to this BSC, we essentially see a thermal photon cloud. And if we put more photons and we reach the condensed phase, we in addition see a peak at the center that we attribute to the BC. And to analyze things in more detail, we look at on spectra. So these are theory spectra up here, and these are experimental spectra. So below the threshold to the BC, we essentially see, also here's the position of the cutoff. We essentially see a Boltzmann-like cloud above the cutoff. So to the left, it's low wavelengths, that is higher photon energies. And above the threshold, we in addition see a peak at the position of the cutoff that they attribute to the BC. So there's more, this was 2010, there's more recent photon BCs at Imperial College by Rob Nyman, Utrecht, the group of Chris van Oosten, and Jan Claers and our chairman have realized their own BC now at Twente University. You will hear about that later in this session tomorrow. Baruch Fischer has a photon BC in fiber, and later today we'll hear experiments by Stefan Barland, who has evidence for photon BC in semiconductor microcavity, and thus experiments on a plasma BC at Aalto University by the group by Tom, who uses dye molecules for thermalization. Okay, now regarding the relation to a laser, also in general, I told you that lasing happens if one has little or no thermalization, which then refers to usual laser theory. We wanted to test the transition between lasing and condensation experimentally. So what we did, we put the pump beam not anymore in the center of the microcavity, but a little bit more to the side to make the initial of the trapping potential imprinted by the mirror curvature, to make the condensed state differing from the initial state more. And what we then see, if we have so all this data is at low for cutoff frequencies quite far removed from the absorption maximum of the dye. So we have little thermalization, and what we then see is that the optical wave packets oscillate back and forth in the trapping potential printed by the mirror curvature. So these are Strickhammer images. So this is a highly equilibrium, non-equilibrium state, mode-locked lasing state. Whereas if you put the cutoff now closer to the absorption maximum of the dye at 571, then we do have thermal contact to the dye molecules. And what you see that after some time, photons accumulate to the center of the trapping potential imprinted by the mirror curvature, and we get a BC. So basically, BC is one can get if thermalization is faster than photon loss. Okay, regarding these dissipated phases and the non-emission phase transition that I will talk about a second. There's one interesting property of our photon condensates that I have to now describe in more detail. That is, it can be a condensate in the Grand canonical limit. And to begin with, let's remind us that usual BCs like cold atoms or polaritons operate with fixed total particle numbers. So one has a microcanonical ensemble where the particle number is fixed. one still can have fluctuations of the condensate state to the thermal cloud, but these are only Poissonian, and the G2 they're relatively small, and the second order intensity correlation at 0 times equals 1. The non-canonical ensemble describes a particle exchange with a reservoir, and it turns out that, well, we can have that in our system because the way we thermalize is we absorb photons by dye molecules, so we convert them into dye excitations, and this if photon emission is emitted, basically this is again converted into a photon and a ground state molecule. So this is a photochemical reaction, and which you can describe in the picture of the system photons being coupled to a reservoir of with which not just energy can be exchanged, but also effective particles. If there's much more dye excitations than photons, this can act as a reservoir, which precisely corresponds to the grand canonical descriptions. And now, if the size of this reservoir is much larger than the photon number, then, well, it's a true reservoir. And for most physical phenomena, it doesn't matter whether you use canonical or grand canonical or microcanonical description, but for the fluctuations of a condensate, there's a big difference because the fluctuations in the grand canonical description, they can in the grand canonical DC they become as large as the average particle number, as I'm indicating here. So the G2 at 0 times is not anymore 1, but rather 2 in the condensed state. So same in the condensed state as in the thermal state. From the theory side, this is old stuff. But well, so with photon condensates, one could see this experimentally in 2014 here by the thesis of Julian Schmidt in our lab for the first time. And what we now more recently did is we looked at these intensity correlations in more detail, also short times. And what you see here is that for this example, for these experimental parameters, we see an oscillation. And now the question is, what is the background of these oscillations? And let's first discuss this. The reason are non-Hermitian properties. So one has to account not just for the grand canonical nature, but also for loss and gain. So we do have, of course, loss also, as one has in a normal laser. In our case, it's smaller, as we'll explain. Well, as I already explained, but nevertheless, of course, we do have loss, and with that, the system Hamiltonian becomes complex. And in general, in such non-Hermitian systems, often exceptional points emerge, and at these exceptional points, this is a typical exceptional points. The typical eigensolutions, if you can change two parameters, then at an exceptional point here, two eigensolutions coalesce. And there has been lots of earlier work in laser physics, also in the field of polariton physics. And what I also should mention is that the group of Peter Littlewood has predicted a non-Hermitian phase transition between a photon laser and a polariton DC. And the question that I'm posing here is whether we have kind of exceptional points in a photon DC. And what I first should emphasize this that we are relatively close to equilibrium, as I was mentioning. So here you see typical spectra, and the black line is equilibrium theory. And on this scale, one cannot distinguish. The reason for that is that we have separated time scales. The loss time scale is 400 picosecond, and this is about 3 orders of magnitude longer than the thermalization time scales, which is just half a picosecond for these experimental parameters. but it turns out that the remaining non-Hermitian properties can nevertheless break time reversal symmetry in a strong manner to change the correlation signals as well, as I showed you, these oscillations. And so the second order coherence can serve as a quite sensitive probe for non-Hermitian properties. And now, in more to look at the origin of these oscillations, we look at the coupled equations of motion for the dynamics around the stationary state. And what you see here, well, n is a photon number, and x is the excitation number. That is the sum of the photon number and the dielectronic excitations. And this is a non-Hermitian matrix where omega is the oscillation frequency, and this is 0 if you have no losses. The reason basically is that in the laser-like equations, there comes then a nonlinear term, and if this is non-zero, then this becomes such a non-Hermitian matrix. And in addition, this here is the damping. And all this dynamics, as the oscillation frequency, that's actually an effect that's also known in laser physics from relaxation oscillations. But here, this is not just you switch on and switching off, but this is stationarily driven by these grand canonical statistical fluctuations. And the schematic phase diagram that looks as follows. So here's an exceptional point. That's the theoretical phase diagram. If the damping equals the oscillation frequency, and if we have the relation frequency is larger, then we are in the oscillatory BC phase. I showed you one example already. Whereas if it's smaller, then we in the bi-exponential phase, and we can tune so by tuning the loss and the average quantum numbers. Okay, we of course wanted to look at the other phase, the bi-exponential phase, and we see this here for smaller photon numbers. So here you see an example for a bi-exponential correlation function, and we wanted to look, of course, at the transition too. And what you see here is both the oscillation frequency and the decay times as a function of such correlation signals, as a function of the average photon number. And you see, so here's the exceptional point where there is this vertical dashed line, and you see that above that, the oscillation frequency becomes non-vanishing, and below that, we get a splitting up between into two time scales. And this phase transition, of course, as I was mentioning, at an exceptional point. And this here is a more detailed version of the phase diagram as a function of both the average photon number and the loss rate. And so here would up here, very much up here would be the crossover to lasing, and here on the right hand side, relaxation oscillation. And this data set you should see here covers this part here. And now more in detail on the phase transition, that's helpful to consider the system eigenvalues. In the oscillatory regime, we have, there's two eigenvalues with a negative real value, and they're split up by the different imaginary values in the complex plane. So we have a gap in the bi-exponential regime. There also is a gap, but along the real axis. And at the exceptional points, the eigenvalues coalesce and the gap closes, and then we become very sensitive. So there's a small parameter variation. Then we very rapidly are in the oscillatory or the bi-exponential phase. And that's what one usually accepts at a phase transition. Okay, this is looking at the phase diagram in more detail. Red corresponds to oscillatory phase and blue to the bi-exponential phase. And if we sample our data along this vertical, within our data along this vertical line, we can also map the transition along the loss axis. So here's the exceptional point. And what you see here, here would be the crossover to lasing. And what you see here is that basically this bi-exponential phase is separated by the point of the phase transition at the exceptional point between both the oscillating phase and the crossover to lasing. Normally, one just has crossover to lasing, and whereas here there's a clear-cut phase transition. So you can argue that this bi-exponential phase is a state of the light that is truly different from lasing. Okay, in my final few minutes, I will briefly talk and experiment on the fluctuation-dissipation relation for such photon condensates. Fluctuation-dissipation relation, that's something very well established for material particles, starting with work of Einstein, who related fluctuations and the dissipation for Brownian particles. So that the relation is given by KBT, but proportionally factor of the thermal energy. Simply the reason being that the fluctuations are driven by thermal energy. There's a more general form by Cullen, Belton, and Kubo. And there were lots of experiments in, well, the last century then, starting with predictions of Johnson on the noise, on the Johnson noise of resistors, for example. Now, right, the question is, can you do so for light? And it was pointed out here by Jacopo Rausotto and colleagues that if you test the fluctuation dissipation relation for an optical quantum gas, this can provide a very critical test of the thermalization. So basically, if you ask a statistical physics expert on whether something is thermalized, the first question that he will ask is the fluctuation dissipation relation fulfilled, and this was basically applied for optical quantum gases here in this proposal paper. And what we do is we correlate the condensate particle fluctuations, the statistical fluctuations of our ground canonical condensates to the reactive response, and so this relates the stiffness of the condensate to parameter formations to the fluctuations, and if the fluctuations are driven by thermal energy, then you will are truly driven by thermal energy, then there will be a relation between those two. So this is putting the same things in more mathematical or quantitative terms. So to derive a corresponding relation, we take the partition function for the photon gas, and by taking the derivative to the dye cavity of this to the dye cavity detuning, so the detuning between our low frequency cutoff and the several phonon line of the dye, we can, well, if you do the first order derivative, we get the average particle number, and if the second, then we get the fluctuations, and by applying these two derivatives, you can relatively easily derive a fluctuation dissipation relation, which relates here the fluctuations to the reactive response, which is the change of the average particle numbers on a modification of the dye cavity detuning. And what that is, that's essentially changing the point of, photons and dye molecules have a slightly different energy due to the detuning. And if you change this detuning, you basically probe the stiffness of the condensate. Okay, so this is the experimental setup that's basically, again, using our microgravity and analyzing the fluctuations with the strict camera, and we also measure the dye cavity detuning and the average partner number with a photomultiplier and the strict camera respectively. And this is now typical experimental results. In the canonical regime, G2 remains very close to unity, and if we tune to a grand canonical condensate, which is a relatively small condensate with respect to the square root of the dimolecule reservoir size, then we have a grand canonical DC that is our photon are bunched. Well, this is from the physics side, basically stuff as earlier, but now we can, as 9 years ago, this old paper, but now we can reach a little bit larger, with somewhat larger G2s. So this is now, this is what you see here in more detail. From that, this is now the raw data where we look as a function of the tuning, both for the average photon number and the average of the square, which relates to the fluctuations. And this is raw data that we need for the fluctuation dissipation theorem. Now what we have to do is relate the square of the average, which relates to the fluctuations, to this right-hand side, to the reactive response. So we have to take the derivative of the average photon number on the cavity tuning, multiply by kVt divided by h bar minus, and you see that both the left and the right hand side here for different tunings, they pretty well lie over each other. So we do have evidence that the fluctuation dissipation relation is fulfilled to relatively good accuracy, and we can also divide that for each other, and this way get the temperature, and this agrees with the environment temperature. This more clearly, this quite clearly shows that the fluctuation dissipation relation is fulfilled, which is a test of the thermal nature of the diameter cavity photon condensate. Now the next question is, how does it relate to the usual form, which relates the RMS particle fluctuations to the compressibility. If you do that, you see again using the partition function that there is an extra term, which is 1 divided by 2 times the effective reservoir size. And in the limit of an infinite size effective reservoir, so in the grand canonical limit, we arrive at the textbook form of the fluctuation dissipation theorem. So this is now plotted. This now plots both the reactive response and the fluctuations versus the dye cavity detuning. And here you see the reactive response if we omit this extra term. In the grand canonical limit, which is here, we obtain the textbook form of the fluctuation dissipation theory. But this extra term is well understood from theory. Okay, so to conclude, I described experiments of the thermalization of two-dimensional photon gas in a dye microcavity cavity and a VC of photons. More recently, we looked at a non-emission phase transition in such a photon condensate, so this is a dissipated phase, and it turns out that this bi-exponential phase is separated by a phase transition to both lasing and then intermediate oscillator phase. And finally, I talked about a test of the fluctuation dissipation theory. And in future, photon concentration could be used for the concentration of diffuse sunlight in principle. I would argue that photon VC photon condensates are a new state of the light field, and some future directions would be to look at the non-canonical regime in more detail. It also would be interesting to look for superfluidity. We know it's a condensate, but we haven't found evidence for superfluidity so far. A very interesting topic would be to look for quantum many body states in periodic potentials. So if you have if you can engineer interactions and if you cool light in a coupled array of microcavity lattice, then you can cool the ground state can be an entangled state, and if you cool or thermalize to such an entangled ground state, you can directly propel that in an equilibrium process, and this is something that you cannot do with cold atoms. There, one first basically has to produce a BC and then ramp into the lattice. And finally, it would be interesting to, with this method, realize light sources in new wavelengths regime, and this way try whether this can be a new way to develop coherent UV sources. And for lasers, it's relatively hard to produce continuous ultraviolet coherent sources, because the spontaneous lifetime, you have to invert, and the spontaneous lifetime becomes shorter and shorter as you go to higher frequencies. Condensate, you don't have to invert the thermalization, medium, and spontaneous emission to a trap. So in principle, it could be easier to realize high frequency coherent sources. And if you succeed in obvious application, would be semiconductor lithography. Finally, I wanted to thank both you for listening and my group. And yeah, thank you.
Thank you very much, Martin. I guess it's time for questions. Are there any questions from
If I may ask a question? Good morning. Thank you very much. Good afternoon, sorry. Thank you very much. Very interesting talk. Very, very convincing. I could ask several questions, but I'll start with a simple one. The first one, you talked about indirectly system size. You estimated at the beginning something like between 10 to the 4 and 10 to the 5 photons. You didn't talk about number of emitters. Of course, in the dye, you have an enormous number of emitters. Depends on the concentration of your dye, of course. Is there a lower limit that you can estimate to the number of emitters? Or let's say differently, I think if I understand your talk correctly, what happens is that if you reduce that too much, you just end up in the vicinity of a regime where you have more losses than what you can gain. And so in some way, you're just getting closer to an equilibrium state, which is closer to lasing. But I think it's a very interesting transition. So I would be interested in knowing how you can quantify these limits.
Yes, as basically one has to, this is given by the issue that you have to reabsorb the photons. So if you don't have sufficient emitters, your photons are not reabsorbed. This is what this is limited by. But this depends on the, on your cavity finesse, of course. If you don't have a high cavity finesse, you need more, and this is what, and it also depends on the absorption cross section. I mean, a second thing is that the fluctuations are then determined by the ratio of the photons and the number of dye excitations. But this doesn't directly influence the thermalization. But right, you do need sufficient emitters to such that you can reabsorb your photons and the thermalization is effective, as we said.
Okay, thank you, Martin. Any other questions? Then, if not,
Well,
Maybe
if you don't have any other, I can ask another one.
Oh,
if you don't mind,
Yeah.
I have plenty of them. But I was very interested in your statement about G2 that tends towards 2.
Mhm.
And my question is, if you come close to the exceptional point, or maybe just beyond, can you have G2 larger than 2? Do you observe anything like that, or do you have an argument against that?
We don't observe anything larger. If it's normal, the argument is if it's statistical fluctuations, the fluctuations, I think, cannot become larger than the average value, at least from the theory. If one looks at it, this turns out to be the maximum. And this depends on the ratio of the photons and the square root of the number of die, the effective die size. So basically, if the effective number of, let's go right here. Yeah. So if here, so this has some effective reservoir size. And what happens is that the Poissonian fluctuations of the reservoir mix into the system. And if the reservoir is quadratically large, then this Poissonian fluctuations becomes as large as the system. And this is how, that's an intuitive way to understand it. So if so beyond the Grand Canonical limit, if the reservoir is larger than the square of the system size, and canonical if it's the other way around.
Thank you very much.
Okay, then I think in view of time, it's best if we move on to our next speaker, it's Antti Malanen from Switzerland, I think, right?
Yes, exactly. Do you see my slide?
I see the PowerPoint. I don't see the presentation. Yeah.
No. Yes.
Yep, that's great. Yeah. Please go ahead.
Yeah, thanks, Chris. So I'm Antti Malanen. I'm currently in ETH Zurich as a postdoc, but I'm today talking about work done in Finland in Aalto University in the group of Professor Päivi Törmä. And we will continue in the topic of Bose-Einstein condensates, and this time in a plasmonic system. So I will just briefly first start by introducing the system that we have been studying, and then I will present you some results of plasmonic BEC at weak and strong light matter coupling regimes, and in the end I will show some recent results about the measurements of the G1 function of this plasmonic BECs. So first of all, this plasmonic lattice is a periodic arrangement of nanoparticles, and when light diffracts in the plane of the array, it gets strongly coupled with the single particle resonances in the lattice. And this leads to a new form of hybrid modes, which are partially photonic, partially plasmonic. And here on the right, you see the dispersion relation of this SLR modes. And if we take a look at the crosscut of the dispersion relation here at the center of the graph, we find that the SLR modes appear as a very sharp, narrow resonance compared to the localized single particle resonances. And the quality factors of this in-plane cavity is typically on the order of some hundreds. And the important point here in this dispersion is the band edge, as we have already learned also in the microcavities that Professor White told about. So it's also important in this system that there is kind of a bottom of the dispersion band that can be utilized for the lasing and condensation experiments. And these plasmonic lattices have been combined with gain materials such as fluorescent molecules and quantum dots, and different groups have observed phenomena that produce coherent light, such as lasing, polariton lasing, and condensation in the strong light matter coupling regime, and also Bose-Einstein condensation, which shows some signatures of thermalization as well. And here are also some photos of the sample. So it's nanoparticle arrays fabricated on glass and then applied some liquid dye molecule solution on top of the glass. So, as I mentioned, many groups have been studying this phenomena of lasing in plasmonic periodic plasmonic structures over the past 2 decades. And in Professor Törmä's group in Aalto University, some topics include, for example, strong coupling with quantum dots and dye molecules. And then we have studied lasing in one-dimensional chains of nanoparticles, as well as different materials such as magnetic materials and dielectric materials of nanoparticles. But today I'm gonna focus on the results of the Bose-Einstein condensate, which was the topic of my PhD thesis in Törmä's group. So the thermalization mechanism in the weakly coupled plasmonic lattice is very similar to that described by Professor Weitz with the dye-filled microcavities. In our case, we don't have mirrors that form microcavity, but the array acts a bit like the mirrors or like in-plane cavity that provides the feedback. So here in the experiment, if we have applied the molecules on the array and we pump from one end, some of the molecules will go to the excited state and they will then decay radiatively and excite the lattice mode, which makes the lattice mode to bring alive and light propagate along the array. And as Martin described, in this reabsorption and emission processes, every time when the molecules get excited, they lose some energy through internal vibrations and rotations, and which means that every time when a photon is emitted from the molecules and absorbed again by the lattice mode, the energy has reduced, and this allows the population of the SLR excitations to thermalize towards the bottom of the dispersion band. So this is indeed has a lot of similarities to these experiments by the Weitz group, where they thermalize by the light moving between the mirrors in the microcavity. And in the experiment, we basically pumped the array, a long array from one end, and then we image the how does the light what kind of signature or footprint does it leave on the array. So here on the y-axis of this graph we have the distance from the pump, and on the x-axis we have the energy. And if we look at the populations at this region of the array where the thermalization has kind of come to some kind of a steady state, and we then take the spectrum unfit Bose-Einstein distribution to it, we find temperatures that are somewhat close to the ambient temperature where the experiments are done. And this was just the first demonstration of the Bose-Einstein condensate, and I will soon show you results in the strong coupling case where this thermalized kind of thermal wing or thermal tail of the population or the Maxwell-Boltzmann distribution is more evident. But I will also here mention that we also simulated this using the Curtin and Keeling model of photon condensation, and we find an agreement with the experiment. But the notable thing here is that the simulations are done in the time domain, whereas the experiment is done in the spatial domain. And we can find a correlation or agreement between these two spatial and time domain if we take into account the linear kind of slope of the dispersion relation, which gives you a group velocity. And if we turn these numbers from the simulation into the distance traveled along the array, we find an agreement with the time scale shown here and the experimental distance. And a few other things that we measured from this first realization of the condensation is that we proved that the light indeed originates from the dispersion of the SLR mode. So here we have measured in the beginning part of the array and in the end part of the array, and we can see in the case-based measurement that the light really comes from the dispersion relation. And we also measured the increase of spatial coherence, and also that with pump probe scheme we showed that this process happens in a picosecond time scale. Now in the other experiment where we have otherwise a similar system, but now we pump throughout the whole array and we image also throughout the whole array, we increase the dimolecule concentration such that the system is now in the strong coupling regime. So here on the right, there's the dispersion relation without the dimolecules and with dimolecules. And we can see how in the case where we have the dimolecules on, the dispersion has this avoided crossing with the absorption of the molecules. And so the system is in the strong coupling regime. And in these experiments, we varied the lattice size and also the pump pulse duration in order to probe the dynamics of the thermalization. So if we look at the light in, light out curve, or the threshold curve, here on the left, we found actually two thresholds that occur consecutively when we increase the pump fluence. And in the first threshold, the system shows signatures of polariton lasing. It's rather large line width in these experiments, but it still shows the signatures of lasing. And especially here in the real space images, one can observe that it almost looks like individual lines of nanoparticles are lasing. And this is kind of also confirmed by the fact that the momentum space confinement occurs only in one dimension at this threshold. Now, when we increase the pump fluence, the system undergoes transition into a Bose-Einstein condensate form. And here in the real space image, we see this kind of more uniform blob of light originating from the central part of the array. And now the 2D case-based image actually shows confinement in two dimensions. And also notable here is that the spectrum of the light shows now quite clear Maxwell-Boltzmann tail of the distribution. And in this intermediate regime, we have the chance to observe what is going on in the thermalization process, because in this regime, the thermalization is not yet complete, but we can see some signatures. For example, here we already see this kind of interference patterns arising in the array, which originate from the light traveling in the up and down directions along the array. And meanwhile, propagating the population undergoes thermalization. But yes, it's not complete at this regime yet, but we can still learn something from this thermalization mechanism. So here I'm showing these real space images and spatially resolved spectra for different lattice sizes. And notable thing here is that if we first look at a large array on the bottom row, we see that there is kind of a darker zone or darker region close to the edges of the array. And we find this distance from the edge of the array to the point where the light kind of comes out, or the pulse comes out. This seems to be constant and independent of the lattice size. And especially if you look at the small array size 40 × 40 micrometer here, it's interesting that the pulse comes out kind of in the opposite sides of the array, and such the redshift of the light also occurs kind of in the opposite direction than in the large array sizes. And we attributed this effect to pulse buildup known from the like gain-switched, Q-switched lasers before. This is just the rate equation simulation of stimulated process where a pump pulse arrives, generates population inversion, and then there is a short time between the population inversion peak and the output pulse. And this is the pulse buildup that we here claim to, that we see this kind of in the spatial signature. So it's again relating the travel distance along the array into the time scale. And so this hints to the direction that in this strongly coupled BEC, the thermalization seems to be a stimulated process, which also could explain why it happens so fast. So here, indeed, by summing up this kind of output pulses, we could reproduce the spatial patterns that we observed in the different sizes of lattice. And another thing is that we also studied this effect as a function of pump fluence, and we found there a similar relation that this pulse build-up time follows in the conventional laser theory. Now, I also want to point out that so the previous experiments in the strong coupling case were done with a very short pulse of 50 femtosecond, and we observed that if we increase the pulse duration to like 10 times longer, the second threshold disappears, and we don't observe Bose-Einstein condensate. So along the pump curve after the first threshold, we only observe the polariton lasing. And this also kind of hits the direction that the process needs very fast excitation, which also means that it has to have very high peak power for the excitation. So in the final part of the talk, I will show a few characterizations of this strongly coupled BEC. And first of all, just as a background for this, in the three-dimensional BECs that are at equilibrium, it's known that off-diagonal long-range order can occur, which means basically that the spatial correlation function can show almost no decay over large distances. Now, in two-dimensional BECs, the Mermin-Wagner theorem basically says that the thermal fluctuations prevent the buildup of this kind of true off-diagonal long-range order, but there is kind of a mechanism predicted by the Brzezinski, and Thules, which says that in the two-dimensional system, through vortex-antivortex pairing, quasi-long-range order can be maintained, and this would show up as the algebraic decay, so power law decay of the spatial correlations with exponent below 0.2225. And in our case, it's the condensate is more in the region of non-equilibrium condensates, and there it has been predicted in the theory that this similar mechanism as the Brzezinski, and Thules predicted that this could happen also in non-equilibrium case, but then the spatial and temporal correlations would show different exponents. And another mechanism that has been explored also experimentally is the Khadr-Parisi-Zhang mechanism, which refers to dynamical ordering of the phases such that the decay of the G1 function would show stretched exponential decay with universal exponents. And there's also some works which say that there can be a crossover between these two last mentioned mechanisms by the system anisotropy, so depending on how anisotropic is the system. So we measured this G1 function using the conventional method of Michelson interferometer using a retroreflector. And here, the contrast of the interference fringes can be directly connected to the G1 function. And in this case, where we have the two thresholds, first one corresponding to polariton lasing and the second to BEC, we are now exploring the region around the second threshold, so the condensation threshold. And here in the middle row, these blue maps are the G1 function in the spatial domain. And we can see from the crosscuts shown in the bottom row that it looks like below the BEC threshold, the correlations decay kind of as a Gaussian way, maybe, whereas above the BEC threshold, we basically see almost no decay along the over the whole array. And if we now fit...
I'm sorry,
yes.
Is it possible that you could wrap up in maybe 1 minute or so?
Yes, this is coming to the end, yes.
Great.
So if we here fit the different functions into these profiles, we find indeed that below the PEC threshold, the decay is Gaussian, whereas above the PEC threshold, we find that the power law and stretched exponentials fit almost equally well. But the exponents that we found from this were not matching any of those predicted in the theory so far. And just as the final note, also in temporal coherence measurement, we found the similar things that above the PEC threshold, power law and stretched exponential models fit almost equally well, and the exponents again did not match any of those predicted before in the theory. And this brings me to the summary of the talk. So we have discovered the Bose-Einstein condensation in plasmonic lattices at weak and strong coupling regimes. And this at the strong coupling regime, it looks like the thermalization could occur in a stimulated manner. And this condensate shows spatial coherence decays up to millimeter length scales. And we find non-exponential decays in both spatial and temporal coherence, but we have not found agreement with the current theory predictions. And that's why in the next steps, it would be important to have some new theory to understand this fast thermalization dynamics, and also to explain the spatial and temporal coherence decays. And with this, I thank you, and I also thank my colleagues for supporting in this work. Thank you.
Thank you very much, Antti. Are there any questions?
May I ask a quick question?
Of course, yeah. I think one question is maybe all we can fit. So
yes, there are many questions, but let me ask this one. There is a very interesting comparison I see emerge between your system, which is a plasmonic one, and a semiconductor polaritonic system or excitonic system. What are the complementarities between the two?
So compared to microcavity polariton systems, at least in our case, the polaritons have this plasmonic component as well, right? So there is some difference in the nature of the quasi-particles that undergo the condensation. Also, in the mode structure, our system is highly anisotropic compared to planar microcavity polaritons. So the modes have these two distinct polarizations that can be also easily manipulated by the array structure.
Okay. Thank you once more, and I think then it might be time to move on to our last talk of the session by Stefan Barlan, but I don't see him in the session yet. That is unfortunate.
And try to email him, but probably won't work. Yeah.
Yeah, I would also think that that's hard to do in this last minute. I can try. In the meantime, maybe I can ask one more question to Antti, if that's okay.
Yeah, sure.
I was wondering for this, and maybe I will ask Massimo whether you can send the email while I ask the question.
I will try to call him.
Yeah, that will
That's
also
much
work.
better.
Yeah, that calling is always especially well. Anyway, okay. So the question about I had that you map this spatial dimension onto, let's say, time effectively in this system, right? And I was wondering, can you do stuff where, for example, halfway through the thermalization, you shock the system into some different lattice or so, and then see how that influences the thermalization, sort of a rapid quench or so?
Yeah, so we were studying this just in different sizes of array.
Mm-hmm.
So kind of repeating the measurement in different lattice sizes. And it looks like one has to really match the lattice size with the thermalization time such that you can observe the Bose-Einstein distribution in the time integrated signal.
Mm-hmm. Okay, so let's say it's sort of a narrow range for us this works.
Yes, exactly. For the strongly coupled case, we only found that that we can observe it in the time integrated signal in like 100 times 100 arrays. So if we go to 60 micrometer array or a large one, 150, then we can see that we kind of it's happening there, but we cannot see it in the time integrated signal. And since everything happens so fast, we have no ways to image it temporally.
Okay.
Yeah.
That clarifies it. Interesting.
Let me say one thing. Sorry, I just was able to reach Stéphane Barlan. He had not seen the program correctly and got the wrong day. So we can continue the discussion.
So he's not coming.
Not at this session, no.
Unfortunate.
Yeah, unfortunate, but we have the time to talk about it.
Yeah, exactly. I mean, that's again fortunate, I guess. So, yeah, no, I also have to admit, I was sweating a little when I looked at the time zone. I was like, wait, what time is it again? But in the end,
yeah, I think he made a mistake in the time conversion. That's the problem.
Yeah, that also could work. Yeah. Okay. So maybe some more questions, maybe for either of both speakers.
Well, I have a question to Martin, if possible. I would like to. Yes. I would like him to come back to the measurement with the streak camera when he was injected. Was injected with a pump which was not at x equal to 0, and he was observing some, let's say, hopping between left and right.
Yes.
So, yeah, can you add more details about these measurements?
Yes. Let me just wait. Can I wait? Here. Right. Okay. Yeah. Right. So what that basically was, what we did is we right. So this was a microcavity. Normally, we have a relatively large pump spot, and for this, we used a smaller pump spot and pump on the side. And then what we saw, this was not hopping. This was so as a function of time, the wave packet was really oscillating back and forth in this potential. One doesn't see that very well here, but the wave packet was, because this thing has a threshold somehow, but the wave packets were oscillating back and forth in the potential, whereas if you have thermalization of photons, then it really goes down to the center of the trapping potential imprinted by the mirror curvature.
So, where you say mode-locked laser state, where you speak about mode-locked?
Okay. Well, in the language of normal lasers, this corresponds to mode-locked states because it's many. I have to lock the phases of very many stationary states to describe such a wave packet.
So there will be which kind of states? The modes of your potential?
The modes of the potential, yes, yeah, which correspond to the laser modes, yes.
Okay, I see.
I mean, a wave packet motion is somehow well, that's a description basically that comes from normal quantum mechanics or atom optics or whatever. But the laser physics language would be mode locked because there one normally thinks in terms of stationary states, and normally, and this is right. And the difference also is this here is a spatial oscillation, and in normal laser. These are longitudinal modes. And
yeah, so it's a transverse mode locking, let's say.
Yeah, it's a transverse mode link. Right, that's the point. Yeah, good.
Okay,
yeah.
Okay, thanks.
Could I rebound on this and ask a complementary question if you want? Would that be the same as saying that this is just a superposition of locked Hermite modes in a quantum mechanical sense?
Yes.
Because in fact, you're breaking the symmetry, rotational symmetry. You have a XY symmetry, like longitudinal symmetry now, if I understand your geometry correctly. So you have Hermite modes, and those are in fact the maximum of your Hermite modes, and in between you have something not very visible. Is that right?
Understand if I understand it correctly, right? It's several Hermitian modes which are mode locked.
Yeah, so it's basically a quantum harmonic oscillator.
Right. Yeah. Right. Precisely. That's what it is.
That's what I was thinking of. Okay.
Yeah.
Fine, thanks.
Okay, seeing this graph again, I kind of have a question because you see light all the way on one side and light all the way on the other side. But you never see it sort of in between while oscillating, or is that?
Right. The reason is the way that the thermalization works probably is dimolecules which sit in the center. They absorb and then they emit down here. I mean, this street camera, it may also be an issue of the color scale. I mean, here you see a bit, and also what one should say, these images, it always becomes less. And these images are normalized such there's a constant intensity all over, always in one line. So this is what one would say. So this one is not the same intensity here and here. Here it's less because we do lose all the time. So it's also an issue of the color scale and the normalization and something like that.
Yeah, and I guess there's mostly not the edges because then the oscillation moves slowest, I guess, in time, or what?
Sorry, I don't understand.
Let's say I don't really see how the normalization then keeps only these maxima, right? Or let's say, why are there these very extreme maxima? I guess in an oscillation, it's always that the photons spend most time at the extreme, right?
That's why. Yes,
yeah.
That's why. That's why. That's why. And if you look at the color scale here, maybe it was not chosen so great because I mean, up to 30 or 35%, there's a zero and so on.
Okay, that would help. Yeah.
Yeah.
Yeah, well, you can see that again as the wave function of the quantum harmonic oscillator. It's the same thing.
Yeah, so I would say that maybe this oscillator state is somewhat of a coherent state superposition, these modes.
Right. That's what it is. Yeah.
Yeah. Interesting. Maybe more questions? I guess we're out of questions, which I don't know. It's always a good and bad sign, maybe. But then maybe we can just end the session a little early here.
Yeah, there is no problem. We can do that.
And then we'll see each other over the next 1 days, probably a few times. So
yes, and this session restarts at 4. It would be
6 p.m.
6 p.m. Normal Central European time, but
correct.
Yes, yeah. So
for us, it's 6 p.m. Yeah.
But if
2 and 3/4 hours, yeah, basically.
Yeah, but if I understood correctly, there's also is there still a plenary session in between?
Yes. It's this section that is restarts at 6 p.m. for us. But there are plenary sessions in between. Yeah, there's one.
Okay.
Thank you very much.
Bye.
Yeah,
Thank you. Bye.
Bye.
Thank you.
Bye.
Thank you.